everyone, and welcome to my channel, Professor Parks PhD. This video is another in my lecture series of the solar system, and tonight this lecture is going to be concerned with planetary atmospheres. What I'm going to do is I'm going to provide a framework from which I can then later talk about the atmospheres of the Earth, Venus, Mars, all of the terrestrial worlds. And so we're going to cover some just basic ideas such as structure of planetary atmospheres. What are they composed of layers? And if so, what are those layers? What does an atmosphere do? And we'll start off by asking the very obvious, but yet not well-defined question: what is an atmosphere? Now, I do want to apologize for those of my viewers who watch these live. This was somewhat impromptu, and it is not, because it is 1 a.m., it is not my typical time to do this. Georg, howdy, how are you? But let's get into this. So, planetary atmospheres. Now, the beginning of this is going to be essentially a recap of a few things that I've been saying over the course of the last few lectures. But what are we, like I said, what are we going to try to do here is, it seems that, it seems that my slides are not formatted very well. Apparently, as you can see, I'm at home. I am doing this on a Linux box, and so the conversion between the open office, I don't know. So hopefully these slides will be clear. The background image is not what I normally intended, but anyway, it is a beautiful picture of the Earth, and you can kind of see the curvature of it. Anyway, what are we going to learn today? We're going to try to answer the question of what exactly is an atmosphere. What part does the greenhouse effect play in warming a planet? The greenhouse effect has been used in a sort of negative connotation because of the whole climate change issue. But the greenhouse effect, as I'll show, is actually beneficial if the effect is mitigated. If in fact it actually has a built-in thermostat that normally keeps it sort of under control, or really keeps it in somewhat of an equilibrium. It's only because of human input to the atmosphere with certain gases that thermostat is kind of broken. Hey, Peter, howdy. I know you're from Australia, so that makes sense why you're up at this hour. And then finally, I'll talk about atmospheric properties like the density and the temperature and pressure, and how these change as you vary with atmosphere. Essentially, how they change as you go from the ground all the way to the furthest extent. So, what is an atmosphere? Basically, at its basic core, an atmosphere is a layer of gas that surrounds a planet. I'll go a step further and define the atmosphere as those particles, those either atoms, molecules, or ions, electrons, protons, that sort of thing. Those objects that are gravitationally bound to the Earth, that they move around the Earth, but do not escape on short time scales from the Earth's gravitational influence. That is how I'm going to define the atmosphere, because later on I'm going to say something about the atmosphere that you may not in fact know, and may in fact have a hard time conceptualizing. But please remember that is the definition that I'm going with, that it is basically a gas layer composed of molecules, atoms, ions that are gravitationally bound on sufficiently long timescales around the Earth. Now, again, this is going to be really a recap of what I've been talking about before, is that the Earth and the terrestrial worlds first started off with primary atmospheres that they gained through accretion, gravitational accretion from the protostellar disk or protoplanetary disk from which they formed. And those primary atmospheres were hydrogen and helium. Now, hydrogen and helium are very, very light gases, and because of the high temperatures of the Earth and the other terrestrial worlds at that time, the worlds were much hotter then than they are now because of the massive amount of energy which was being released because of the accretion and differentiation processes that were happening at the time. And so the hydrogen and helium quickly thermally escaped. They were given enough energy that they had speeds higher than the escape values of their individual planets. And so they quickly lost, again, quickly from an astronomical point of view, quickly lost their primary atmospheres. And in fact, and so they developed secondary atmospheres, and these secondary atmospheres were the result of essentially outgassing. What I mean by outgassing is through either cracks, tectonic cracks, the surface of the world literally cracked open, and trapped gases from the accretion process were released. Primarily, these gases were carbon dioxide, nitrogen, and so forth, and then also volcanism, basically volcanic eruptions that spewed out, again, these trapped gases from within. Additionally, you had a contribution. Now, how much of a contribution is still something of an open question, but cometary impacts also provided, we believe, most of the water content that the Earth and these terrestrial bodies may have had at one point. Now, previously, I've explained why the Earth appears to be the only planet that has a liquid water has liquid water on its surface, particularly in abundance, and that is simply because of the strength of its atmosphere and the temperature of its atmosphere. At this point, again, as I've mentioned before, Mercury and the Moon basically have no atmosphere. Basically, again, the first order. They do technically have atmospheres as I've defined it, but as we'll see, they are very, very tenuous in nature. Venus and Mars, Mars has a significant-ish atmosphere, significant enough that the actual date or the daytime sky is in fact a solid color as opposed to being black, but it is again pretty tenuous. Venus obviously has a overblown, has the thickest atmosphere of all the terrestrial worlds, and obviously we're all hopefully fairly familiar with the density and thickness of the Earth's atmosphere. Now, the Earth's atmosphere is around 10 kilometers thick, and again, I say this, but really what I mean is this is when I say the atmosphere is 10 kilometers thick, really what I'm going to be talking about, or what I'm referring to in that sense, is the troposphere. Really where all the action's at, where the weather is, everything that we care about. Basically, the part of the atmosphere that is even remotely habitable, or is and even remotely habitable to humans without the need of, say, an environmental suit. It is primarily composed of molecular nitrogen and oxygen, with smaller constituents of carbon dioxide, argon, and a few other elements. Now, as I'll talk about, the actual size of the atmosphere is much larger. Again, based on the definition that I gave previously. Let's talk about atmospheric pressure. Atmospheric pressure is different than gas pressure, in that with gas pressure, essentially you need a container, but there are the certain principles still do apply. With gas pressure, what you have this is an example. You have a balloon, basically gas which is contained. You have gas inside the balloon, and then you have gas that's outside the balloon. And what this is saying is that if you have a balloon of a certain size, then you have, this is what we call a equilibrium position. The balloon is going to stay at that size unless it's interfered with in some way. Again, on short order, balloons can be pretty porous. As you might notice, holiday balloons, birthday balloons will eventually shrink down and fall onto the ground and so forth. But on short order, what's happening is that the gas inside the balloon and the gas outside the balloon, those are composed of molecules. And those molecules are moving with respect to each other due to the respective temperatures. And as they are moving, they are slamming into not only themselves or each other, but they are also slamming into the container itself. If the pressure exerted by those pounding pounding molecules inside the balloon is exactly the same as the pressure of those molecules on the outside smacking into the balloon, then the balloon is in like I said, what we call equilibrium, hydrostatic equilibrium. When you inflate that balloon, when you add more gas into the balloon, what you are doing is now there is more gas inside the balloon. Those additional gas molecules are going to slam up against the walls. It's going to create a larger pressure, a larger force per unit area than on the outside. But ultimately, if you stop continually adding molecules to it, it's going to equalize. It's going to essentially keep a set size, and again, that size is going to be based on the force or the pressure being exerted by the interior molecules with respect to those in the interior. So you can increase essentially the size of something by increasing the volume, or you can increase the size of the container by increasing the volume, the amount of molecules, the number of molecules inside that volume. You can increase it by that pressure. Or, and this is why hot air balloons work, is what you can do is you can heat the balloon. And when you heat the balloon, you're primarily heating the molecules inside that balloon. And if you add that heat energy to those molecules, they're going to be absorbed and they're going to move even faster. So thermal energy is akin to the energy of motion, or kinetic energy. So the more energy and the hotter something is, the more the molecules that comprise that object are moving around. And the faster you're moving around and you slam into something, hopefully you can conceptualize that there's more momentum there, there's more oomph, and there's more force. And so that pressure, again, is going to get larger. But ultimately, it's going to get to the point that if you continually heat the balloon, it's going to get larger and larger. And if there is enough energy put into this thing, then it's going to essentially pop. But if you stop applying the heat, then the molecules are going to stop expanding, and they're going to stay at a particular temperature until they basically cool off. This is why, if you've ever been in a hot air balloon, I used to crew for a hot air balloon, so I'm pretty intimately familiar with this. In order to get it to rise up to altitude, you have to apply the flame. You got to basically just hold on to the burner and just keep that sucker going. But once you get to altitude, then you can release the burner, and for a while you will essentially stay at that rough altitude, given wind conditions. But eventually that heat is going to radiate outward away from the balloon, and it's going to begin to sink. And so occasionally you have to apply a little bit more heat to keep yourself at altitude, or if you want to go up to higher altitude. This is analogous, but not quite the same thing as to what's happening on the Earth. Because when you have gas pressure like this, When you get into an equilibrium state, the pressure density of the pressure gradient within the volume is pretty constant, because they're typically, when you're talking about gas pressure, you're talking about small containers or relatively small containers, certainly very small in comparison to the Earth. Now, with the Earth, the container, as it were, is in fact the planet's gravity. The planet's gravity is the pressure, as it were, of what's keeping that gas localized around the Earth. If very much like, I take my iPod or AirPods, I throw them up in the air, gravity is going to pull them back down. With the molecules that are flying around you at this present moment, they have the potentiality to be going in a direction that would take them away and take them into space. But if they don't have a certain velocity, they are going to get pulled down, and they're going to change their direction, and they're going to come back down. More often than not, they will probably get hit. They will hit something, and they get redirected into a random direction. But ultimately, as a whole, the gases stay around the world because, howdy, Nimrod. The gases stay around the world because gravity is keeping them in place, keeping them surrounded around the Earth. So, however, the difference again between atmospheric pressure and gas pressure is that with atmospheric pressure, because of the fact that the container-ish is gravity, you're going to have a pressure differential. You're going to have a pressure gradient, excuse me. Again, because gravity is related to the distance square or inverse distance squared, the closer you are to the Earth, the more the Earth's gravity is going to essentially slow that upward motion, is going to keep them in down. And in addition to that, you have the weight of the upper atmosphere with respect to the lower atmosphere. That weight is coming down, and as you move upwards through the atmosphere away from the Earth, you have less stuff up here, you have less mass above the stuff below, and so that's going to create a smaller gravitational pressure than if you experienced here. The best explanation, or a great example of this are pillows, and I think you can do this in your room if you've got enough pillows. Maybe your significant other loves pillows, so if you take them off the bed and you stack them, what you should notice is that the bottom of the pillows at the bottom are compressed more than the pillows at the top, because again, because of the weight of all of the pillows, the bottom pillow experiences a larger gravitational force from all the pillows above it, whereas the pillow above it is only experiencing the atmospheric pressure, the pressure from, or the weight of the atmosphere itself, which as it happens at ground level is surprisingly not that much. It is, as you can see there, 1.03 kilograms per square meter. If you're an imperialist, it's 14.7 pounds per square inch, or if you're a meteorologist, 1 bar. That works. Make things way easier. Now, where does the atmosphere end? The atmosphere, there are a couple of different ways you can define the atmosphere. As I said, you can define the atmosphere as I did a moment ago, and basically just refer to it as the troposphere. I mean, it's essentially, from a human perspective, we're really only interested in the troposphere because that's where we travel, essentially. But if you're interested in getting a nifty NASA astronaut badge, then what you have to do is you have to go above, I believe it is 80 kilometers. I could be switching this because you have two demarcations. You have an 80-kilometer line, which is either NASA or the European Space Agency, or 100 kilometers, which is also called the Kármán line, and then that's the other one. And for the life of me at the moment, I can't remember which one's which. I'm most familiar with the Kármán line at 100 kilometers, and that, I will freely admit, is arbitrary. That is 100 kilometers is a round number, so sure, why not? At that point, you're talking about an atmosphere which isn't breathable. You wouldn't be able to see it. It's very, very rarefied. You're talking about maybe 100 atoms or hundreds of atoms per cubic centimeter. Again, really not that dense at all. And beyond the Kármán line, you have space. However, that's not exactly, if you go to the strict definition that I had at the very, very beginning, which is the particles that are gravitationally bound. What we have found, and actually we knew this for a while, we had the data for a pretty long time. It wasn't until someone actually went back through archival SOHO data. SOHO is a satellite that's been operating for a couple decades now, if not longer, that has been solely looking at the sun, and that's all it does. It just stares at the sun. Well, I guess it also does look at other places because of this graph, but primarily it just stares at the sun. And archival SOHO data has shown us that, in fact, the Earth's atmosphere actually extends about twice as far as the moon. So you can say, again, with the strict definition that I stated in the beginning, that the moon is traveling through the Earth's atmosphere. But when I say atmosphere, again, this is what's known as the geocorona, and it is very deformed due to the sun's pressure. So the geocorona is much less dense much more dense on the day side than it is on the night side. On the day side, it's around 70 atoms per cubic centimeter. On the night side, it's 0.2 centimeter atoms per cubic centimeter. I mean, again, you have to go to 5 cubic centimeters in order to get one atom. So, is that an atmosphere? Technically, sure, why not? I don't know. Yeah, they were on 100 kilometers. Nice round number. That's that, as far as I know, it was the thinking behind the definition of the Kármán line. I do not know of any other physical reason for why that line exists. But what are the effects of the atmosphere? Well, there are a number of things that the atmosphere does. The atmosphere contains pressure, and so that allows for water, in particular, to be of a certain phase. If, for example, on Mars has temperatures where liquid water can exist. So we often think of phases, liquid, solid, gaseous, in terms of temperature, because we're most familiar with environments on the Earth. So essentially the pressure is pretty much always going to be the same, unless you stick it into a vacuum chamber or what have you. But in everyday life, we're familiar with things like boiling water on the stove, snow coming down from the sky. And so again, that's all pretty much the same pressure. But if you go to Mars, which has a significantly less pressure than the Earth, then you can have a temperature where liquid water can exist, but it doesn't. If the pressure is low enough, then the water will immediately evaporate. It will boil and evaporate very, very quickly. So that is the primary reason why Mars does not have any liquid water on its surface at the moment, because of the fact that the atmosphere is so little, or so small, so thin, that the pressure is not great enough that even if the underlying ice would melt, rise to the surface, it would immediately boil off. Atmosphere will also absorb, refract, and scatter light. The atmosphere, and particularly the constituents of the atmosphere, are what determine its color, as I'll describe later on. The atmosphere also contributes to wind. Obviously, wind is the movement of air. If you don't have an atmosphere, you can't have wind. It also determines the primary. Again, this might seem obvious, but it contributes to weather and it also contributes to climate. It can interact with the solar wind and create a magnetosphere. Really, because the magnetosphere, again, if you want to call it, it is part of the atmosphere. But when I'm thinking of the atmosphere, again, I'm only thinking of the gases. But the gases can get trapped or get frozen into the magnetosphere, the magnetic field of the Earth or the planet. And as that magnetosphere gets distorted by solar wind, that can also create distortions in the atmosphere. This is most notable with SpaceX. About a year ago, there were a number of their satellites, about 48 of their satellites, got deorbited because there was a disturbance in the force. There was a disturbance due to both geomagnetic and also stellar, kind of a stellar storm or solar storm. In any event, the magnetosphere caused the atmosphere to actually balloon outward, and so that created enough atmospheric drag to deorbit, or basically cause Starlink satellites to crash into the Earth's surface. And then finally, the greenhouse effect, which I'm going to hopefully to convince you that the greenhouse effect kind of gets a bad rap. The effect itself is actually really, really nice. Carmen found that 99.9% of the Earth's atmosphere is contained inside a layer of a 100-kilometer thickness. I did not know that. Okay, so maybe it is physically motivated. That would make sense considering it is named after someone. Thank you, Georg. So let's start off with the greenhouse effect. What is the greenhouse effect and what does it do to a planet? Obviously, as by this question, which hopefully you can see. Again, I do apologize for the formatting of these slides. I was just working on them and I can tell you they were not this. They were a black background, not the Earth. Anyway, the greenhouse effect will warm a planet. In basic terms, what the greenhouse effect does, what the greenhouse effect is the atmosphere trapping heat for some period of time close to the surface of the Earth. So let's talk about visual light. Visual light, of all of the wavelengths, visual light is the most energetic that actually reaches down to the surface of the Earth with any sort of quantity. Ultraviolet light does get down, but thankfully for us, because of skin cancer, not a lot of the ultraviolet light actually manages to get through all the layers of the atmosphere and get down here. So so most of the energy that the sun puts out that reaches the Earth's surface is invisible light. So when it hits the Earth, that energy hits the Earth and it warms the Earth up. Those photons carry energy. Those hit the molecules of the Earth, causing those molecules to move faster and warming them. But because if you remember back in my light lecture, I like to say that nature is lazy. If you add energy to the system, if you add energy to the Earth doesn't want to be hot. It wants to cool off. It wants to be at a lower energy state. It wants to lay down on the couch. And so it's going to re-radiate that energy as infrared radiation, or traditionally known as heat. Now, infrared radiation passes through the atmosphere differently than visible light. Visible light essentially goes down straight. Now, there are effects. It does kind of plinko its way down which causes twinkling and things of that nature, but essentially it comes straight through the atmosphere. Infrared, really not so much. If you're talking about infrared as a whole, as opposed to specific bands or specific areas within it. The infrared radiation is going to pass upward. It's going to try to leave the Earth, but certain elements, certain molecules within the atmosphere are very good at absorbing and redirecting that infrared light in a different direction. So what that means is that heat is trying to get out, but hangs around for a while. Ultimately, it does escape because obviously, if it didn't leave, the energy of the sun is coming in. The energy of the sun is not ending. We're constantly getting energy from the sun. So if the atmosphere did not release that energy, eventually we'd all cook. So, common greenhouse gases are methane, carbon dioxide, water, and nitrous oxide. Now, real quickly, for the 4 people watching, which of those gases is the most efficient at producing a greenhouse effect? Or no, I take that back. I take that completely back. Which of those gases produces the largest greenhouse effect? I'll wait. And for the folks at home, if you watch this later, feel free to guess. Which of those gases produces an overall, each of those gases warms the Earth a certain amount. Which of those gases produces the largest warming effect? Such that if you were to somehow Thanos your way into removing that gas, the Earth's atmosphere or the Earth's surface temperature would drop dramatically, the most dramatically. Peter Noddle says methane. Nimrod says methane. Peter says methane. Nimrod says methane. Now, I may have tricked you, or rather, I may have misled you. Actually, the gas that contributes the most to the greenhouse effect is actually water vapor. Water vapor is the worst greenhouse offender, if you want to go with that. The reason why we don't talk about water in terms of climate change is that humanity really isn't changing the water content of the atmosphere. It's still pretty much, no matter how much you drive around, no matter how much you drive around, no matter how much coal you burn, water is pretty much going to stay relatively the same. And you will probably correct me on this, but methane actually would have been the answer at the for my very first question. Methane, of all those gases, is the most efficient. It produces the largest increase of temperature, or it traps more heat per unit molecule than any of the others. It's certainly more than carbon dioxide. And nitrous oxide, I have a feeling I might be wrong, and it might be more efficient than methane. But I can say that methane is a much more efficient greenhouse gas than carbon dioxide or water. The reason why it is not the thing that we focus on the most, we often focus on the carbon dioxide as the most, is because methane is in so much smaller quantities overall than carbon dioxide. Howdy, Dan. It's actually the morning for at least guessing two of my guests, or two of the people watching. So again, this is another schematic that shows that you have incoming visible sunlight passing through the atmosphere. It heats the ground. The ground re-radiates that energy as thermal energy or infrared light. the atmosphere is more opaque to infrared light, and so that those photons, that heat, basically hangs around for a while until it eventually escapes. But ultimately, the Earth and all other planets get into a thermal equilibrium. Because, as I said, if it didn't, then either the Earth would continually freeze until it was just an ice cube, or it would heat up to the point that it blew up. So it reaches an equilibrium temperature based on a number of different factors. And without the greenhouse effect, as we'll see later on with a table, the Earth would actually not be habitable if the greenhouse effect were not a thing. The Earth's temperature would be far lower, definitely too low for liquid water to exist, and thus too low for water to exist. Too low for liquid water to exist, and therefore, as far as we know, life could not develop. So, this is essentially a definition of thermal equilibrium. Simply put, it means the amount of temperature or amount of energy being absorbed by the Earth, the amount of energy that is being absorbed by the Earth is equal to the amount of energy that is being radiated back out into space. The key term there is the amount of energy that is being absorbed by the Earth, not the total energy that is incident upon the Earth's atmosphere. How much of that energy is actually being absorbed and then regurgitated out as heat. One of the determinants of that equilibrium temperature, of that surface temperature, is obviously distance. Energy, light, or the energy or light, and the energy there carried by that light drop as the inverse square. You sort of a very common sort of or form of how things dissipate over space. So if you have a certain bubble and the light hits it, and you have a certain area of that light, if you double the size of that bubble, in order to contain the same amount of energy as that first part, or on the first bubble, you have to the area has to be 4 times larger. So the light diminishes by a factor of 1 over r squared. Or if you were twice as far away from the sun, you were receiving 1/4 the amount of radiation than if you were at, just a set distance. So ultimately, what that means is the further away you are, the colder you are, the closer you are, the warmer you are. The other issue is reflectivity, or what we refer to as the albedo. The albedo is simply a percentage of how much energy or how much light gets directed out as opposed to being absorbed, how much of that energy or light is being transmitted inward. The higher the percentage, the higher the albedo, the more reflective it is, such that if if something has an albedo of 1, then, or 100, depending on how you look at it, like 1 really, then it reflects all the light. The atmosphere is essentially a mirror, or the planet is essentially a mirror. If you have an albedo of 0, then your object is black. It basically reflects nothing. It just absorbs anything. It's essentially a black body. Obviously, there is no example of either of those two extremums in the solar system. Venus has a very, very high reflectivity, or very, very high albedo at 0.7. Which is kind of counterintuitive and kind of amazing considering its surface temperature. Its surface temperature is, as I'll show in a moment, and as I've mentioned before, really, really high. But the reflectivity, the reason why the albedo of Venus is so high is because of the clouds. Because of the clouds that are contained in its thick atmosphere, about 70% of the light that hits the atmosphere of Venus actually gets reflected outward. It does not go to the heating of the planet in any real significant way. I honestly don't know what the albedo of the Earth is. I want to say it's around. I'm not going to make a guess. I'm not even going to make an estimate. But the Earth's reflectivity obviously varies based on how much precipitation is trapped in the atmosphere, how much clouds cover there is, and so forth. In fact, one of the ideas, pie in the sky ideas, which I have ethical problems with, to mitigate the greenhouse effect or climate change, is actually cloud seeding, is to create more clouds by putting in some kind of, I think it's ammonium sulfide or something in the air to basically cause clouds to form. The idea there is you increase the reflectivity of the Earth, more incident light gets reflected away rather than getting absorbed, and so forth and so on. Does that include all spectrums or just visible light? I think what you mean by that question is, does visible light only contribute to global warming, or does all spectrums do it? Technically speaking, any incoming radiation over all wavelengths is going to, if it gets deposited on the Earth, it's going to contribute to a hotter temperature of the Earth. It's going to heat the Earth in one form or another. Shorter wavelength light, gamma rays, X-rays, and ultraviolet will do so at a greater, to a greater effect than, say, radio will. Radio really doesn't, heat much. Microwaves, though, actually do a really good job of heating water, but I digress. The reason why I've been focusing on visible light is those higher frequency wavelengths. Most of those get blocked by the atmosphere. If you want to get very specific, the atmospheric albedo actually is wavelength dependent. If you're talking about gamma rays and X-rays, the albedo is actually nearly 1. Those rays don't actually pass through the atmosphere and hit the Earth, which makes X-ray and gamma ray astronomy especially difficult. UV is slightly less. UV, a little bit of it actually manages to pass through the atmosphere and get to us, hence sunburns. Visible light, no problem. It hits the Earth, no problem. And if you look at the energy that is being emitted away from off the sun, most of the energy that the sun emits is in the visible range. Now, when you get into radar or radio or infrared and radio and so forth, then is it 0.3? I was thinking 0.25 actually. So hey, I was not that far off. Awesome. But for some reason in my head, it was like, no, that's more like the albedo of the moon. But so obviously I was thinking incorrectly. Anyway, so to answer your question, visible light is the primary way that the energy from the sun gets transported to the Earth. Gamma rays, X-rays do not penetrate. UV doesn't penetrate as much, and also in comparison, there's not a lot of gamma rays and X-rays that are being emitted off the sun in comparison to visible. And then you have the same thing on radio and infrared. Is not a lot of that is being transmitted to the Earth as opposed to visible light. You also have to think about when you're talking about atmospheric or surface temperature, you also have to take into account rotation. What rotation, the way that rotation matters, and really this is also coupled with a significant atmosphere. Because if you have just in general, or just, yes, if you have a world that has a significant atmosphere, like the Earth, an Earth type atmosphere, if it is slowly rotating, then you're going to have a higher temperature differential between the day side and the night side. If you have a rapidly rotating or comparatively rapidly rotating planet, then you're going to have energy transfer. Essentially, the energy that it gets from there's going to be stronger air circulation, and so that energy that gets deposited on the day side will be more efficiently transported to the backside. And so the temperature differential for for that world is going to be, from day to night, is going to be less. But it gets a little complicated when you get to the extremes. If you have if you have a planet that has very, very little atmosphere, there's very little heat transfer. I mean, there's a little bit in terms of basically the rate at which the world will dissipate that incoming energy. But for the most part, there is no heat transfer. And so Mercury, for example, has almost no atmosphere, and so therefore the day-night is extreme. You have hundreds of degrees Celsius on the front side, a negative 140, I believe, degrees Celsius on the night side. But then you have Venus, which again is bizarro, in that Venus's rotation is actually longer, significantly longer. I think it's over twice as long as the orbital period, or the year. Its rotation is around 270 days. It's exceedingly slow rotating. But because the atmosphere is so thick, it transfers that energy very efficiently. So it doesn't really matter if you're on the day side or the night side of Venus. The temperature is going to be a lovely 400 degrees Celsius year-round, every day, wherever you are. Yes. Dan, if you can fit, in fact, 63 Earths inside Uranus, if you relax. There's actually, I put it on my Discord. I think I put it on my Discord. There's a store in the city or town of Uranus, Missouri, that is a gift shop, and it produces fudge. So the best fudge, and its slogan is, the best fudge comes from Uranus. And if you go to the website, it basically just Uranus puns from top to bottom. I mean, it gets ridiculous after a while. So anyway, that reminded me of that. Getting back to atmosphere. So here we go. Here we go. The reflectivity. So according to this particular textbook, which is 21st Century Astronomy, Mercury has an albedo of 12%. Venus has an albedo of 73 or 75. I can't read that from here. 75%. The Earth is 29%. The Moon is 12%. Mars is 16%. We can look at the no greenhouse surface temperatures. Mercury would be 163. Venus would be minus 40, Earth would be minus 16, and so forth. Mars would be really, really frigid. But again, this is the average surface temperature. Obviously, if you look at the day and nighttime cycle, the daytime of Mercury is 425 as opposed to negative 175 on the night side. Venus is actually warmer than I expected. It's 470 degrees all over the place. So Venus, despite being the second planet away from the sun, is actually still the hottest planet in the solar system. The Earth's average temperature, at least at the time of this writing, is 15 degrees Celsius, and so forth and so on. And the Moon, being very, 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 very similar to Mercury, also has an extreme day-nighttime cycle. And on the last column, you can see how much the greenhouse effect, or the greenhouse warming, has contributed to the rise of the overall temperature. Again, for the Earth, it's probably a little bit more, by fractions of a degree centigrade now than it was at this writing. But anyway, so how do the atmospheric properties vary with altitude? And this might surprise the layman, I guess, or someone who is not familiar with the atmosphere. And to a certain extent, it is also somewhat counterintuitive. But hopefully I can convince you of certain things. So before I can do that, I need to basically talk to a certain extent about the phase of gas, or phases of gas in a way, but really, what does light do to to gas or to atoms. I talked a little bit about this in my light lecture, but let's start off with very low energy gas. So when you have very low energy gas, what can happen is it can be the atoms, or rather the molecules, will absorb infrared light effectively, and it will then re-radiate that light in a random direction, as I described with the greenhouse effect. Now, if we raise the temperature of the environment, then what you can have is scattering. The visible light will hit the atom. The visible light with a certain amount of energy is going to hit the atom or come near the atom, and it's going to essentially get it's going to scatter around it or get refracted, and it's going to refract more. The refraction is wavelength dependent. Bluer light is going to get refracted more than red light does. You can if you continue to raise the temperature, you're going to get something called dissociation. The energy of the average photon is going to be high enough that it's going to break the bonds, the chemical bonds that are holding molecules together. And so the individual atoms are going to be freed, and they're going to fly off into space. You might still have a smaller atom or a smaller molecule fly off. What I'm thinking about is ozone, for example. Ozone, when it breaks up, it's composed of 3 atoms of oxygen. When it breaks up, typically what you get is an oxygen atom flying out, single oxygen going this way, and then an oxygen molecule, O2, flying off in the other direction. If you continue to, and that's called dissociation. So when you destroy the molecule, you disassociate it. You can continue, if you continue to raise the temperature, you can ionize the gas, where now you, instead of splitting apart a molecule, you are essentially splitting apart an atom. You are splitting the electrons away from the protons. So what you have left is, instead of, say, neutral hydrogen that's flying around, you now have protons and electrons whizzing around at fairly high rates of speed. So ultraviolet light and X-rays can easily ionize and dissociate molecules. Molecules tend to scatter, as I said, they tend to scatter more blue light than red light, and molecules, as I've already mentioned, can absorb infrared light with a certainly high efficiency. Now, the atmosphere is complex. It's ridiculously complex, but very much like the Earth's core, the interior of the Earth, which is also very complex. I'm going to simplify it down. I'm going to simplify it down to 4 layers. Now, I'm going to skip the mesosphere. I'm not going to talk about the mesosphere. What I am going to talk about are the troposphere, the stratosphere, the thermosphere, and the exosphere. And so, troposphere. The troposphere is the lowest layer of the Earth's atmosphere, and it's, roughly speaking, 10 kilometers thick. This is where all of the fun stuff happens. This is, like I said, this is where where convection occurs, where the convection occurs. This is where the greenhouse effect happens. This is where all the clouds are, the hurricanes, the tornadoes, all of that. All of that is inside the troposphere. When you look at the temperature profile as a function of altitude, what you find is that the temperature decreases with altitude, as we normally expect. The higher up you go, the colder it gets. Next layer up is the stratosphere. And in the stratosphere, we have what we call a temperature inversion. Now, the temperature and what I mean by a temperature inversion, actually, we technically have 3. You have a temperature inversion at the boundary between the troposphere and the stratosphere, where instead of the temperature decreasing with altitude, it actually increases with altitude until you get around 50 kilometers or so. And then it inverts again. Now the temperature actually decreases again as you get higher up. And then there is another inversion just above, I guess it's just above the stratosphere in the next layer up. It's funny that you should mention ozone, because I was going to ask folks, what is at 50 kilometers, that is roughly 50 kilometers, that is causing the temperature to be weird like that? Well, what it's and that would be the ozone layer. So you have ozone again is O3. It's three oxygen molecules, and it is really good at being dissociated by UV radiation. So let's look at this temperature profile from top down. So when this light comes in, it typically is, like I said, well, it's ultraviolet. Ultraviolet is relatively high energy radiation, or high energy light. It's containing a lot of energy. It has a large capacity to heat things up. So as it passes through, the way that it heats things up is by interacting with the molecules, by either ionizing these molecules and breaking them apart and causing them to move at fairly rapid speeds, or or disassociating these molecules into smaller constituents. And again, the temperature or the thermal energy, the kinetic energy of the particles increases. So if we go from the top of the thermosphere, you have the most UV radiation hitting the stratosphere. If we take this top of the stratosphere, you have the most UV radiation smacking into the stratosphere. And as it does so, it's going to heat the gas. It's going to heat the upper stratosphere, and as it continues to go down, more and more energy is going to be thrown into the mix. And the reason why the temperature increases is because you are now getting to a layer where you have more and more O3 existing, until you get to a point where you're essentially stuck in the middle of the ozone layer, or you're dead center in the ozone layer. You have the thickest amount of it, and that essentially acts as a barrier. This is really what prevents most of the UV from coming down into the earth or hitting the earth and giving us all skin cancer in minutes. Is that most of the UV light at this point gets absorbed in the process of disassociating the ozone layer, or destroying the ozone, and basically no longer existing. So fewer and fewer UV light is penetrating completely through this ozone layer, and then that causes the temperature differential to drop. So now, as you decrease in altitude, the temperature will drop because you have less and less UV light slamming into the atmosphere, causing it to heat up. Now, why? Now, of course, the UV doesn't completely destroy the ozone. It doesn't. It is not completely efficient. Obviously, ozone exists. We managed to keep it around by no longer having hairspray, inconveniencing people in that way, because of the fact that that oxygen atom and that oxygen molecule, they really, really like each other, and eventually they're going to find each other or find another partner, and they're going to hook up. And so it's just a constant sort of recycling of UV radiation comes in, breaks an ozone into pieces. Those pieces go find other pieces, create ozone, and they absorb more UV or different UV radiation, and so forth and so on. Then we have the thermosphere. Now, the thermosphere is called as such because the energy profile or the radiation profile ramps very high, to the point that you can have thousands of degrees. The atmosphere can be thousands of degrees Celsius. Now, the reason why things don't melt, for example, the satellites or rockets, they don't melt as they pass through the thermosphere, is because again the atmosphere at that point is exceedingly rarefied, um, as Georg was kind enough to point out. Once you get above 100, 99.9% of the atmosphere by mass is below the Kármán line at 100 kilometers. So you're getting into maybe a few hundred, or maybe at the lower level, a few thousand atoms per cubic centimeter. So this brings us to the idea of what exactly is temperature? What exactly do we mean by 1,000 degrees Celsius? What we mean is essentially the kinetic energy. What is the average kinetic energy that these molecules have, or these atoms have, or ions at this point have? And when you look at the amount of the average kinetic energy, that translates to a temperature. Very much like when we talked about the black body curve, the amount of energy that that a star emits. Where was I going? That corresponds to a certain temperature. So the energy of motion, temperature, in what we in a strict sense, is directly proportional or directly related to the kinetic energy of the gas. When we think of heat, we think of it in biological terms, in the sense of and I'm not a biologist, so I'm not exactly certain about what it is about our skin that does this. But there is a sufficient number of molecules, or sufficient number of molecules traveling at a sufficiently high rate of speed that we interpret that as heat. The total amount of energy is higher. We gain a higher total amount of energy because there is simply more molecules traveling at that velocity than there are if we are at the thermosphere. So when we talk about the sun, I'm going to talk about the sun's corona, which is 1,000,000 degrees Kelvin. But again, it's exceedingly rarefied. It's ridiculously rarefied. So the chances of you actually hitting or the amount of times you're going to be hit by an electron that is 1,000,000 degrees Kelvin is really rare. It's very, very rare. And so the amount of energy that you're going to get per impact is actually going to be very small, which is why things don't melt at those temperatures. So I know that it might think, you might say, oh, at 1,000 degrees Celsius, this such and such metal would melt. Well, that would be true if you had as much if you had as much molecules at that temperature bombarding that object as you have on the ground. But because you don't, because it's so rare, because there are so few molecules to transfer that heat or transfer that energy, things don't melt. And then you have the exosphere, which again is even, technically speaking, is even a higher temperature. But as I've already mentioned, the exosphere is the most rarefied. You're talking about maybe tens of or less atoms per cubic centimeter. And it is warmed by X-rays and UV. So so at this point, you're really talking about there is some neutral hydrogen that still survives at these heights that can extend beyond the moon. A lot of that, or a significant portion of that neutral hydrogen, does get split up, does absorb X-rays and ultraviolet rays, and gets split up into protons and electrons. And so the exosphere is primarily composed of positive and negative ions, but there is a little bit of neutral hydrogen still in there, because again, things attract. So the electron and the proton, as they fly around, they're electrostatically, they're going to come together again. They're going to fairly soon get broken apart by an X-ray, but they're going to find somebody else and pair up again. So I'm going to end this lecture by talking about why is the sky blue on the Earth and why is the sky black on the moon. And really, when I say the sky is blue, really what I'm talking about is the daytime sky, because the sky is not always blue, as hopefully we all know. The reason why the sky is blue is because our atmosphere is primarily composed of nitrogen, nitrogen gas. Nitrogen gas has a property that it scatters visible light very, very well through a process called Rayleigh scattering. And that causes, so you have visible light streaming down as a beam. So it's what we call plane parallel, but essentially you can think of it as a beam of light coming from the sun with an angular size of, half a degree. It hits our atmosphere. That visible light, the blue portions of that visible light, well, all of that light gets refracted. All of that light gets refracted into random directions. Blue light gets refracted at a higher rate or by a higher amount than the red light does. Which is why when you look at the sun, which I don't recommend, but if you look at the sun or the area around the sun, it is more whitish. And then as you move away from the sun, you are seeing more blue. The sky is bluer because as you get closer to the sun, you get more of a contribution of the yellows, the greens, the reds. But as you move away, you're getting less of that contribution. And so you get more of the blue light. Yes, Peter, they are promiscuous. So that is why essentially the blue light, the atmosphere or the sky appears blue because the sun is here. It's bringing light this way, but then it hits the atmosphere, sends light that way, sends light this way, sends light that way, and it hits my eye. So I can get blue light from every direction I look at because the light, which originally came from this small area in the direction of the sun, hits that atmosphere and gets redirected everywhere and then redirected back to my eyes to see it. Why are sunsets red, generally speaking? Well, there are two reasons for that. The first reason, which doesn't really relate to refraction, is actually absorption. The atmosphere contains molecules, and more specifically, rather, it contains dust. Dust absorbs red light way more efficiently than it does, it absorbs blue light way more efficiently than it does red. So if you don't even think about refraction at all, the dust is absorbing, basically, is getting rid of that blue light, and only allowing that red light from the sun to actually come and hit your eye. In addition to that, the dust will re-radiate that energy again as heat or infrared, and you'll get a little bit more red. But the other reason related to this refraction, the other reason why it's more red is because of the fact that you're only getting basically half of the refraction effect. You get most of the blue light, or a good fraction of the blue light actually gets refracted out into space and not to your eye. And so you remove that blue light from essentially the equation, and you see the sun as more reddish than not. So it's a combination of those two things. It's a combination of the fact that you were looking through less atmosphere than, well, ish. You're looking at you're looking at only basically, the atmosphere that is at you is the ones doing the refracting. You don't get sort of back refracting. I don't know. I'm not really explaining. Hopefully you get it, because I'm not finding a clear way to explain that very well. But anyway, a lot of the blue light gets refracted elsewhere. You can also think of it as if you are, say, you're a person at noon at Hawaii, the light comes down. No, that doesn't work either. So yeah, basically the blue light gets scattered, but also because of the dust content in the atmosphere, you also get a lot of blue light that's absorbed. Now, why is the moon black? The sky on the moon black? It's because of the fact that There is no atmosphere. There is nothing there to scatter the light. So all of that light is coming down, is beaming from an area that is essentially one half a degree in the sky. And so it's beaming down onto us. And so there's no light coming down, hitting anything, getting redirected into this direction, then redirecting back to you from this side or that side. So you only see the light from the sun in that localized area. And I can imagine it's bright as F, because you essentially are getting all of that energy. None of that energy is being dispersed around the atmosphere and hitting you. It's all coming from that source, which is probably why the astronauts wore shielding. You never see the astronauts' face because they need heavy shielding, because that is a tremendous light source on there. And also the moon's reflectivity is high enough that the light from the ground is also pretty damn bright, which also leads into photographs of Apollo. There are folks out there who believe they're like, where are the stars? You should be able, the Earth, obviously the Earth and the sun and the solar system are surrounded by stars. So where are they? Well, you have to understand there's something called dynamic range with photography. With film photography, with digital photography, there is a certain range from being able to see your brightest brights and your darkest darks. High dynamic range on a television is a great example of this. And so what we're seeing is that we are seeing only the brightest of what's in this image. So right here we have the moon, we have the Earth, and I think this is called Earthrise. It's actually been tilted. I think the original photograph taken by the last name starts with the B, can't remember it. Anyway, the original photograph is actually tilted this way, but this is the classic, or the famous moonrise photograph. So what you have is obviously the moon. You have the Earth and the Earth that's further on, and you do have stars further away. But if you look at the brightness of those individual little stars in comparison to how bright the Earth is, and then also how bright the moon is, the film just doesn't have the dynamic range to capture those very faint background stars. It's not saturated. That's not really the right word, but it doesn't have the ability to image essentially those really bright brights and against those really dark darks. I think it is kind of like glare in a way. If you have a light that's streaming at you, if you're have headlights coming at you, you can't really see what's beyond that. It's not that you don't get the photons from the back of the car or the top of the car. Those photons are reaching your eye, but your eye is being essentially overwhelmed with the massive amount of photons that are hitting you from the headlights. So that's why you don't see stars in Apollo photos. And you probably won't see stars when we actually start sending probes to the moon with digital cameras, which sadly the Japanese failed to do this morning. According to what I've heard, the commercial Japanese satellite that was supposed to land on the moon smashed into the moon and blew up. So they lost communication. Tyson says you should be able to see stars on the moon because you can see them when they get high enough above the Earth. I don't know about visual observations. Like if you were an astronaut I don't know what Armstrong saw. I don't know what Buzz Aldrin saw. If they standing on the Earth's surface or the lunar surface, if they looked up away from the sun, if they could see stars, I don't know. I've never heard reports of it. But I can, like I said, I can tell you that the reason why you do not see stars in photos is because the film isn't capable of recording that sort of that sort of faint stars against the background, or against that bright planet. Um, but howdy, Rachie. Thank you for being here. And howdy, science. Um, if you look away from the surface, your eyes could adjust to see them. Again, I don't know. Obviously, I've never been on the moon. I've never been on the moon. I've never heard any of the astronauts being asked that question. So, oh yes, yes. I know Tyson. So, well, I know what Tyson has said. I don't know the man personally. There are ways to find bright stars in the images with sheds loads of mathematics. Yeah, you know, I would imagine there's a way, because again, the photons from the stars are hitting the medium. I'm trying to think of whether or not techniques like maximum entropy deconvolution would, or any kind of deconvolution method or algorithm would actually tease out those stars. But I know it would cause the image to be, it would increase the resolution of the objects, which would cause the brightness to be more centrally concentrated. But yeah, I don't know. I don't know. Don't get rough started on NDT. Yes, yes, I know. Not going to. No, I certainly don't know everything. I wish I did, but I don't. So, well, actually, no. I wish I knew a lot. I don't know if I wish I knew everything, because then things would just get boring. Because then I can learn. All right. So that is the lecture du jour. Next time, hopefully, later today. It's 2:30 basically here right now. So I will go to bed. I will get up at 8, teach physics, and then hopefully later in the day, I will do another lecture, and that lecture will talk about the atmospheres of the other worlds. Mercury, Venus, Mars, so forth. So, and then after that, we'll talk about the Jovians, which are basically just atmospheres, kind of, sort of. All right. For those of you who are interested, I am going to shut this down, but I am going to go live right after this because, yeah, there's a reason why I am up at 2:30 in the morning. But that's neither here nor there. If you care about that sort of thing, please stick around. If you don't, then thank you for watching this either live or on Memorex. I hope you found it educational. I hope you have also found it entertaining. If you like this sort of content, please subscribe, like, share, subscribe, and hit that bell for notifications, because I do not put out videos on any kind of ordered time frame. I will put them out whenever I can. So hit that bell for notifications. If you'd like to support what I do here, or what we do at GMU, please consider becoming a patron of mine, or hitting me up on PayPal, what have you. I did buy more lights for the dome, or for the dome. I'm now I'd like to get some focal reducers for our telescopes, so that we can actually observe visually. We can observe open clusters, things that are many degrees in size. Right now, our field of views are limited to about the size of the moon, which most open clusters are much larger than that. Nimrod, I'm I'm feeling worse. which again I'll get into in the next one. So, but yeah, so yeah, I will see you all later. Peace out, and I hope you all have a good day wherever you are. So, bye bye.